Okay, so thank you, first of all, of course, for giving us the best paper award. We are very happy about that. This is a working collaboration with some people of my university, actually, of my lab for web algorithmics, and with people at Facebook I'll explain you how this started from the first pass. So the general idea we are pushing, the agenda we are pushing is that when you want to study how a huge graph is made, like a large social network, essentially you can do something local, like looking at the degree distribution, maybe clustering coefficient, triangle counting. That depends on the local structure of the network, like the neighborhood at distance 1. Or you might want to try to look globally at the structure of the graph, and a very natural candidate is the distance distribution, when you want to understand how a graph behaves in a large, in the large somehow, and the graph is too big to actually like being simply drawn, or other indicators doesn't really tell you what's happening. I mean, it's one of the many things you can look at, but it's somehow the simplest thing you can look at that is really global. I mean, it's very difficult, for instance, to fiddle with models to generate a given distance distribution. It's very easy to fiddle with models and get a clustering coefficient or degree distribution you want. To get the distance distribution you want is completely, we don't know. We have very simple examples, but we actually don't know. So what is the distance distribution? So the distance in a graph, say graph social network, nodes and arcs between nodes, possibly directed, is just the length of a shortest path from X to Y. So the smaller number of passages you can do to go from X to Y. It's 0 from X to X, because you can go from 0 to X, from X to X in 0 passages. With respect to your successor or our neighbors is 1, and then you go on. Notice that in graphs that are not strongly connected, there must be pair at infinity. Okay, so pairs that are actually not connected at all, in this case, distance is considered to be infinity. Notice that this is an actual distance. Satisfies the triangular inequality, okay, even with infinity inside. It actually works as a distance. Of course, if the graph is undirected, it's symmetrical. But this is not true in general. Okay? If the graph is directed, it might be possible that dxy is finite and dyx is infinite. So for every t, you should count the number of pairs xy such that dxy is equal to t. So if we want to find the number of pairs at distance 1, 2, 3, 4, and so on. Of course, the pairs at distance 0 and 1 are very easy to find because they are the number of nodes and the number of arcs in the graph. But then you must do something more complicated. And if you instead consider the fraction of pairs, so instead of the numerosity, the number of pairs at distance t, you consider the fraction of pairs at distance t, you get a probability mass function of a distribution, which is the distance distribution. So the distance distribution tells you which fractions of pairs are exactly at distance t. Okay? This is the main idea. You might have heard of this, of course, under another name, which is a degree of separation, which means I have two persons and I want to find the minimum number of intermediaries that I need to get from one person to another person, given that each person along the chain is friend with the person just before and after in the chain. The idea was made famous by a story written in 1929 by the Hungarian author Frigyes Karinthy. It was positivism. Everything could be made into a number or something. So in the story, actually, there is a guy who challenges his friend to find any two people that cannot be connected with more than 6 intermediaries. Okay? Of course, the number in the story, it's actually a maximum. It doesn't work like that. There are people that are much farther apart than 6 degrees. But the name stuck, and the fact that the Milgram's experiments in the 60s gave more or less the same number, of course, consolidated this idea. And then there was John Ware's play, and if you have seen it, Fred Chapise's movie, 6 Degrees of Separation, in which was, by the way, the first movie in which Will Smith starred as he was a main character. Notice a small off by 1. Two friends are at distance 1, but have 0 degrees of separation. Okay, there is no intermediaries. As all off by 1, this turns out to be very nasty, and there are a lot of mistakes in paper because people copy the result from here to there and forget that the two notions are actually slightly, but unfortunately, different. Okay, what we did, simply we took this algorithm and associated software, which was developed at the Università degli Studi di Milano in our lab. It's an algorithm and associated software that computes a distance distribution of very large graphs. I mean, really, really large graphs on not so large hardware. And actually, we presented this at WWW 2011, and in the best possible scientific tradition, during the talk, I said, oh, it would be nice to run this on Facebook. And here we are. We ran it on Facebook. Lars was present during my talk, and he said, well, we should try to collaborate on that. And then Johan was added to the team, and we did this, what I'm going to tell you now. So it was really like a collaboration starting at a conference. So I guess everybody knows about Milgram's experiment. Who doesn't know about Milgram's experiment? Not the one about faking electroshocks to people, the one about chains. So everybody knows. So I'll do a very quick roundup anyway. So the paper is Travers and Milgram 69, and so they did that. They examined 296 pairs of people, okay, divided in 3 groups, and of these pairs, the second element was fixed. So there are 296 people, and a single person that must receive some postcards. And what they did was to ask people, please send this postcard to this person you don't know by sending it to your friend that you think will be closer to get the postcard to the final recipient. Okay? So in this way, they got chains of friendship that were going from these 296 people to this single recipient, which was a stockholder in Boston. Note that what they actually measured thus is the length of a path, a possible path of friendship, but not the shortest path. Okay? So they know, this is a source of a lot of confusion in the literature, even recently, so I'll underline this. Milgram and Travers are perfectly aware that this is an upper bound. I mean, at the end of the paper, they actually state, unfortunately, this is an upper bound. If we had a more detailed description, we would get better results. Okay? So what we did was actually this. Using Facebook, he had a more detailed description of the friendship between people, and we tried to get a more precise result. Said that, the notion of friendship used in this experiment is wildly different from the notion of friendship that you can find in Facebook, because people in Facebook have sometimes very weak links with people they are acquainted with. So there are these two different aspects to take into consideration. Consider also that only 22% of the pairs were actually measured. The other one never ended. So actually the experiment is on a very, like, 1/5, like 60 pairs of people. So we did 250 million billion pairs, so it's more. The average distance found was from 5.4 to 6.7, depending on the group, because the groups were chosen to highlight different things like geographic location, profession, and so on. But I mean, this consolidated somehow the number 6, clearly. Okay. Of course, we are not the first people doing this on social networks. So Leskov and Horvitz found 6.6 degrees of separation, so distance 7.6, on a communication graph of Microsoft Messenger. So it's 100 million persons which have one link between them if they communicated within the last month. Okay? You got 1.3 billion edges. Notice it's very sparse. It's like degree 7, okay? And they get 6.6. It is known from various sources with various variations that Twitter has an incredible small number of, of degrees of separation, but there are 2 problems here. The first one is that the network is highly disconnected. So there are a lot of pairs that are not connected at all. And this is a problem because all I'm telling you is about reachable pairs. So when people say the distance, average distance is such and such, they are telling something about the reachable pairs, so the pair for which there is a path. But they are forgetting all the pairs that are at distance infinity. So in our case, for instance, for Facebook, this is not a big problem because 99.9% of Facebook users are in one giant unique component. With Twitter, the situation is very different. So there are various ways to approach this that I'm not going to talk about, but this number for Twitter should be weighted with the fact that all pairs are actually infinity. If you take the median, for instance, accounting for infinity, it's significantly larger. Also, there is a problem that the MSN Messenger or our experiment, the links must be created by both people. So you talked with someone, he wanted to talk to you. You're a friend with someone on Facebook, he wanted to be friend with you. On Twitter, you just create a link. I mean, if I and 10 friends work a little bit, I think we can lower down this to 3 or 2, just by creating the right links, because everybody can create a follow link without permission from the guy on the other side. So our largest data set is actually 700 million people and 69 billion of friendship links. So it's one order of magnitude larger. And this was also the challenge from the computational viewpoint. Cool. So what we did was to segment Facebook in time and space. So in time, we just took snapshots of Facebook in various moments at the 1st of January of several years. And then we have a current snapshot, which is a little bit off because it was created when we were working in May 2011. Also, we divided Facebook regionally, and this is a little bit more flaky, unfortunately, because the division is based on the current geographic location of the users, because we don't have information about the past history of the user, if I'm correct. So the geolocation, okay, Johan is here in the audience. If you have a question about Facebook, you should ask him. But nonetheless, in particular for the recent graphs, I mean, it's very reliable. So without much more ado, let's see what happens to the distance distribution of Facebook. So this is Facebook in 2007 as you see that there is an initial enlargement, but then it consolidates very strongly with distance, the mode being 5 in a high spike, which means 4 degrees of separation, by the way. Again, this is distances, but degree of separation means 4. And it's incredibly concentrated, and actually 92% of users are within 4 degrees of separation. I mean, if you do the percentile curve. If you look, however, like at Italy, first of all, in Italy in 2007, there was nothing. So this curve is meaningless. Most pairs were actually unreachable. But as soon as people get in, well, you get the same situation, but just moved one step away. So geographic location helps. This is actually 3 degrees of separation. A spike is on 3 degrees. And so, yeah, I mean, we knew obviously geographic co-location helps, but it helps a lot. I mean, it helps by 1 degree. And the same happened in Sweden. We saw exactly the same kind of change of shape. And everybody asked why Italy and Sweden, because we are Italian and Johan and Lars are Swedish. That's the very simple explanation why we chose these two countries. So this is a overall a view, just what happens of average distance. So the average degree of separation, if you take away 1. Okay, there is a transient up to 2008, and you should not really look before 2008 at the graphs, because the problem is that there were so many disconnected pairs that the average is not reliable. I mean, in a completely disconnected graph, the average is 0, but it doesn't mean that the graph is very connected. It just means that you're forgetting all pairs because they are all disconnected. So what we see is that even if the graphs themselves get larger and larger, the average distance gets lower and lower, and apparently there is a kind of stabilization going on in the very last part. And you can see that Italy and Sweden are quite stably slightly below distance 4, so degrees 3. But if we combine them and look at the at the edges between them two, we get a significant higher value. So yeah, there is some importance in geographical concentration. Also, if a country is very, very larger, I mean, you get a little bit higher average distance. But finally, when you go to the entire Facebook graph, this is the number that we get. I mean, the average distance of 2 users on Facebook is 474, which means 374 degrees of separation, which we kindly approximated to 4. So just to be clear, no, we didn't approximate 474 to 4. We approximated 374 to 4. And this must be very understood because the New York Times was so nice to quote the number wrong, even the paper edition. So no, it's not 474 degrees, 374 degrees. Well, what can you do? I mean, we tried our best, but unfortunately. So, other things okay, as I already said, this is meaningful because it actually matters almost all possible pairs. 2 minutes. Okay. Okay, that's more or less it. I mean, there are a lot of more data in the paper, by the way, like we discuss the evolution of the average degrees versus the density. So the average degree is constantly increasing, but the density as the ratio between the arc, the friendship link, and the possible friendship link is constantly going down. And possibly this will stabilize at some point because we are uncovering the real friendship graph more and more, and the more you do, the higher degree you get. But clearly, this will never be 10,000. We'll never have 10,000 friends on average. That won't happen for anthropic reasons, like we will never have pixels where 100, we'll never have graphic cards with 1,000 bits per pixel. It doesn't, I mean, your eye stops at about 30 million colors, so it's useless. And the same happened here. Just as an anecdote, we computed the diameter, so the maximum distance for the recent graphs, which is interesting. I mean, like there are people distance 40 degrees away. So there are people that are actually very far in the graph. Simply, they don't really change the mean because they are very rare, okay? But you can see that there is a difference, again, between the United States or Italy and Sweden and Facebook. And to do that, by the way, we used a very new graph called iterative fringe, a very new algorithm called the iterative fringe upper bound technique that makes it possible to compute the diameter of very large, I mean immense graph, because it just does heuristically like 3 or 4 visits and stops with giving you the diameter. It's actually quite magical because in theory you should do n visits to compute the diameter of a graph. So, okay, I'm almost over, but let me just mention this. Our original interest from our lab was that we are studying the index of dispersion of the distribution, which is the mean to variance ratio, to try to tell the difference between web graphs and social networks, which are both product of human activity, but they are very different. And actually what happens is that if you draw a graph and you place, this is a graph by size and index of dispersion, the red stuff is all social networks and the blue stuff is all the web graphs. We have a bunch of data you can access to and you can reproduce easily these results. So we wanted to know whether Facebook was, okay? And, okay, yeah, it's very low. I mean, it's really below 1. So essentially, the distribution of distances of social networks of people are unbelievably more concentrated, less dispersed than web networks. And that was confirmed by the experiment we did. So you can do it yourself. This is available as free software. You can just download it. And there are also many social networks you need to download and experiment with at our lab if you're interested. And actually, we tried to distribute all the possible data associated to this paper. We cannot give you the Facebook graph, okay? But you can download all the distributions, even the degree distribution, and do more experiments or verify that our statistics are fine or stuff like that. Every single line of code that has been used to produce this paper is available online as free source, as open source software. Okay, I'm over.